Today we're going to do biomass heating of greenhouses. I'm going to cover mostly solid biomass, but I do have a few slides on oils that we'll cover as well. Before I go any further, the other thing is if you want the handouts, if you got a feedback problem, if you go to the button on the right side, it says feedback. Shows a green block. If you point down on that, there's some other messages you can send to me. The other, if you come over 2 buttons from that, there's a group of papers. That's where you'll find the handouts for today. So there's a slide set, and there's also narrative. If you want the complete the PowerPoint of this slide set, you can email me and I will send it out. It's too big to post, unfortunately. And then if you come over on the left side, if the Q&A, if you've got a question, you can type it in. Or you can speak up and we'll try to handle it as we go. Today we're going to cost biomass heating. I've got some product names and pictures and stuff, so I have to disclaimer that the fact that because I mentioned them does not imply we recommend or not endorse other products. So what are we going to cover today? What is biomass? We're going to look at types of fuels for combustion. I didn't change that. I have a couple on biomass. We're going to talk about what's a boiler and what is a furnace, the difference. We're going to talk about outdoor wood-fired hydronic heaters or boilers, which become popular in recent years. We've got some stuff about pellet, grain-fired boilers and furnaces. We'll talk about some standalones, and then we're going to follow up with a case study on 2 greenhouses, 2 different-sized greenhouses, and what their options were, and how it panned out economically as well. So first, biomass fuels. Basically, the definition is a fuel that's derived from plant matter. So it can be wood, that's the most common, been used for years. It can be grains. It can be byproducts like cherry pits or sunflower hulls. It can be, if you're on a phone, you can mute it. I'm getting some feedback, so if you can mute, that would be helpful. Also, it could be crop fodder, corn stalks, soybean stubble, it can be straws, and it can be oils. And we'll talk about the different types of biomass-derived oils. So we can use these things directly. For instance, wood and grain can be used directly. Some of these items are bulky, so things like straw and prairie grass, hay, they can be used directly, but they're better off densified in some manner. It depends on the type of stove you have as to whether you can feed them in bulk. Of course, we got biomass or byproducts, cherry pits, sunflower hulls, nut hulls, rice hulls, are all some possibilities. And processed fuels, so they can be processed from oils or sugars. So one of the things that the USDA is working on is to try to produce cellulosic ethanol or ethanol from cellulosic materials. And the picture in the background of this is Miscanthus giganteus. This is a warm season grass. It's a sterile hybrid. Down in the University of Illinois has been doing work in this area on growing it. I think they can get about 15 tons per acre on this, one cutting a year. And it'll grow up in Wisconsin. I've got some, but we don't get quite the tonnage. So some material characterization. These materials are handled differently, and so we've got different units of measure. It can be volume. It could be cord, which is a volume. It can be by weight, tons or pounds, gallons. So we've got different units of measure. Moisture. Moisture can have an influence on these. It reduces, the higher the moisture, it can reduce the energy content. And in order to burn something, we have to evaporate the water to initiate the burning process. So it takes energy to evaporate the water, so that's a loss from the gross energy that we could use. Now, the energy content is typically in BTUs per unit of measure. And if you look in the literature, you'll find there's a low heating value and a high heating value. The low heating value is an energy after moisture is evaporated. The high energy value is if the moisture can be condensed after combustion. So we look at where that high heating value comes in handy is if we have a, say, a high efficiency furnace which has a extra heat exchanger that condenses out some of the flue gas, the moisture out of the flue gas to capture some more energy. That's where you might want to know what that high heating value is. These materials come in different sizes and shapes, and that may influence the feed system to your boiler. And there's different ash contents. You know, in wood, you'll find anything from 0.5% ash up to maybe 6% ash, just on different types of wood. When we get to grasses, we're going to find that chlorine content is an issue. And it's an issue because it can corrode the combustion chamber. So for types of wood fuels, one is that the energy content will vary with moisture density and ash. We have basically 4 different types of wood that are typically used. We have cordwood, which is traditional. We have green mill residue, supposed to be hogged bark and wet sawdust. Typically it's over 20%, and it can be stored outside in piles. You know, if it rains, it's going to grab some moisture, but not quite as much. We have dry mill, so this could be shavings from, say, furniture factory and stuff, or a sawmill. Planing operations where it's less than 10%. And most of the wood pellets that are made today, that's what's used. And we have wood chips. This can be whole wood, whole trees chipped up, or it can be, you know, limbs and stuff. Here in the city of Madison, they're urban woodlands. They gather the brush and stuff or limbs and chip it up, and people can use it, and it can be burned. So direct use with wood, it's typically sold in cords of wood. So a cord is a volume unit measure. It's 4 foot by 8 foot, or 128 feet. Should be. There's an error. The moisture as harvested is about 50%. We need to air dry it to 20% or less. And depending on the type of wood, it may take a year or 2 to do that. The energy content will vary with species, mainly because it varies in density. Excuse me. Kind of the rough average is about 22 million BTUs per cord at 20%, but it can range from about 14.5 to about 30,000 or 30 million BTUs per cord. The density varies. So, for instance, basswood, the 2,100 pounds per cord, versus hickory can be 4,100 pounds per cord, so almost twice the amount, based on the same volume of wood. All wood is about 7,000 BTUs per pound at 20%. So it's just that if you've got lighter wood, you've got to twice the volume to get the same amount of weight. So direct use. One of the things I like to talk about is people say, well, I got a woodlot, it's free. Well, it may be lower cost depending on what you charge for your labor, but it's not really free. It's actually pretty labor intensive unless you have machinery. Typically, to get the wood from the field to where it's used, it's handled 3 to 6 times. You got harvesting, you got cutting, transport, split, pile stack, and then feed to the take to your boiler, feed into it. Air drying takes a minimum of 1 summer, and 2 is better. So you got to plan ahead. You know, a year or 2 ahead too. You got to labor to refuel. There's systems that I'm aware of that'll automatically fuel cordwood, and you've got ash disposal. Now, it's a much reduced volume, but you still have to get rid of it somehow. That fertilizer content could be spread on the field. And some of these boilers are basically very high emission. There's regulations on their use in certain areas. So that could be an issue. The other would be green wood chips. They are low cost. Usually you only use them if they're locally available. They're bulky. Typically the energy content is going to be much lower, about 4,500 BTUs per pound, because they got to drive off a lot of moisture before it's going to burn. It does have the advantage that we can handle it bulk, so it can be done with augers or conveyors, or bucket loaders. It can be piled outside or in a bunker or covered, depending on your type of system you have. But because of the bulk, you're going to need to, you either have to have space or you've got to have somebody that's willing to provide it in a timely manner as you need it. So corn would be the next topic. And the green mill wood would fall kind of in the wood chip area. It's a little drier, but it's going to be chipped up and used in bulk. So corn, the unit of measure is usually either bushels or pounds or tons, depending on how you sell it. So if it's in bulk, it's usually bushels, although it could be weight in 40 or 50 pound bags, depending on the distributor. Corn, when it's sold or traded, is traded at 56 pounds per bushel at 15.5% moisture. So if you go to a feed mill and say, I want a bushel of corn, basically it's going to be, it may be a little drier, but probably 14 to 15% moisture at that weight range. Now, at 15%, it doesn't actually really burn that well. So some retailers will dry it down to 12 where it burns much better. And you can see the energy content here can be from about 6,800 at 15% to 7,100 at 12%. So you actually get a little more heat content on it. You're going to expect to pay a little more for it because they've had to put some extra energy in it to get it dried down. Some of the advantages of corn, it's readily available. There's no processing. It's an annual crop, so it's easy to get a hold of. The disadvantage is it leaves slag or clinkers, which is the biggest problem you have with it. And basically it's liquefied ash, and then it solidifies as it cools. You have to have dry storage for it. Typically it's going to be a bin. You typically need some wood pellets to get it to start burning. And there's a higher rate of flame outs with this because of the higher moisture rates. The other disadvantage today is that we've got corn selling for $6, $7 a bushel, so it may not be as cost justified as using a wood pellet, just because of the cost and competition for the grain. But some companies will buy a grain that's not fit for animal feed, and maybe got heated or something, so it may be out of condition grain that they will use for this. Now, there's other grains that also can be burned, and here's a list. We got wheat, oats, barley, rye, even soybeans and sunflowers. And these are the trading weights and moistures that you would expect that if you went into the feed dealer that they would, that's the trading weight that would be used. So how do we calculate heating values? And this goes for, I've got it here for corn, but it would go for wood as well. If you know the dry bone weight or dry bone energy content, and this can be done on a calorimeter. So for corn, it's about 8250 per BTUs per pound. Well, if I have 15% moisture, basically I've got 85% corn and 15% water in that product. Well, the water is going to require a minimum of 1,050 BTUs per pound to evaporate, so I can easily do that because I take my 0.85 times 8250, subtract from that the amount of energy to take the 15% of water out, and you end up with 6855 BTUs per pound. So that would be my net, or my low heating value. So that's just an example of how that would be calculated. In a furnace, there are other losses from heat transfer and air and stuff, and typically you're going to find efficiencies around 80% for a well-built, high-efficiency type boiler furnace. Densification. We talked about some of these products are very bulky, so they can be densified. We have a project here at the University of Wisconsin where they're looking at the picture in the upper right corner, where we're looking at making pellets, and this is actually using an old machine that used to be for pelletizing alfalfa for feed that we've been using to try to see if it will work for densifying in a field. So that's an example of canary grass, and they're looking at other products as well. So densifying, what are the advantages, or why would you do it? It facilitates handling and reduces transportation costs. You can use use byproducts that are low value products. You can mix them a couple together, and you'll get a uniform product. You can use bulk handling typically, depending on the size. You do need dry storage because if these things get wet, they start breaking apart. The biggest advantage, you can do automatic stoking. If you've got something in a cube, this size cube up here is about the size of a coal nugget, so it could be run in a coal furnace, so that would be an advantage in a boiler. Typically, they'll have lower emissions because of the uniform product, and they can have high thermal efficiencies, typically 80%, but with small pellets, there are some stoves that are in the 90-plus range, some stoves that come out of, or boilers that come out of Europe. They are higher cost, and they have higher energy inputs to make them, so that would be a disadvantage. For densification, you can do small pellets. They're typically about 5/16 what you buy, about an inch to an inch and a quarter long. So this would be upper right-hand corner would be a picture of what the typical pellet stove would use that you might use in a residential situation. The other would be using cubes or briquettes, which would be used for more of an industrial operation. So that would be down here in the lower right. So those are basically used in industrial boilers. And again, they can use a wide variety of products in them. So some of the materials we'd use in wood pellets would be sawdust or wood residues. So say a planing operation that's making boards would have a lot of wood residue. They can use it. And there's competition for those products with the animal industry that uses sawdust or wood chips for bedding. Typically it's sold in tons or pounds, and either in bulk or 40 to 50 pound bags. Moisture will range from 6 to 10%, depending on the grade, and there are grades through the Pellet Fuel Institute. Typically it's about 8,000 BTUs per pound, and there's different grades. It goes from utility to super premium, and it basically relates to the ash content, going from 6% to the range. And the biggest advantage is it's a uniform product, so it's going to burn fairly uniform. And if you want more information on the standards, I've got the link here on the bottom for the standards. The biomass pellets, there are some companies out there making pellets out of biomass. They can be prairie grass, switchgrass, miscanthus, any kind of hay, straw, fodder. You know, you can put nuts, hulls in it, could add some wood residue, you know, kind of a mix of whatever happens to be around locally. Usually this is sold in tons or 50-pound bags. The moisture is higher. It's typically 8 to 11%, and the energy density is going to be about 7,200 to 8,000 are the ones that I've found available. The ones that are 8,000 are going to have more wood content in them, and the ones that are toward the 7,000 mark will have possibly less or little wood content. Chlorine content in these products becomes more of an issue. Grass has a higher chlorine content. If you let it senesce in the fall and harvest it in the spring, when it's dry, you'll have less of the chlorine content. But it's a problem because it's a high-temperature corrosive agent, so it can corrode the boiler over time and increase your maintenance or shorten the life of the product. And basically, with a Pellet Fuel Institute standard, is a maximum of 300 parts per million is what their standard is. So here's some pictures of the difference. So we got corn, we got some wood pellets. Here's some biomass pellets, and you can have got a grower. This is actually from a grower that does organic. He uses rye and vetch as a cover crop every couple of years, and then he harvests the grain and uses that in a little pellet stove in his greenhouse. So what is a boiler versus a furnace? We often use these words interchangeably. A boiler is going to heat a fluid. It can be water, a glycol water solution. It could be steam. And the fluid is pumped to location typically where it's used. Now, the steam will move by itself, but typically it's going to be pumped. A furnace is going to heat air, and it's going to be blown through ducts to whatever location it's going to be used. So the pictures I've got here, on the left we've got an outdoor hydronic heater or boiler in a greenhouse. We can have a pellet furnace. This happens to be one that'd be add-on for a residential place. And then on the far right is a pellet boiler. The boiler is on the left here, and the bin to hold keep the pellets dry. Some of the advantages of a boiler is you only need one unit, can handle multiple greenhouses. So you have a unit, you pipe the water, the hot water or glycol solution to the different houses. It's an excellent way to do underbench or in-floor heating, although you can supplement it with a water-to-air heat exchanger. They can be located outside the greenhouse. Most of these are weatherized, so you can maximize your growing space. You don't have them in the greenhouse. And they can be in a central location with one fuel storage. So you've got them in all different buildings, and you've got to truck fuel all over the place versus having them in one place. And the other thing that some boilers, one of the things you can do with a boiler to get some more kind of level off peaks and valleys is to have a tank that you have, you kind of store some extra heat in. I'm going to show you a picture of this in a little bit. So that can be an advantage because you can't do that necessarily with a furnace. A furnace has the advantage that it heats air directly, so you reduce one air exchange or one heat exchange. They're typically located in or adjacent to the greenhouse, so it can take up growing space. You don't have to worry about leaks, though, with water pipes or glycol solution. You will probably need multiple furnaces per greenhouse because some of these smaller ones don't have very high BTU output. But that also can be an advantage because then you have a backup if one happens to go out. And you need multiple fuel storage and labor to fill the furnace hoppers. So Can be, but not necessarily a disadvantage. So I want to talk a little bit about emissions. This has become a bigger issue, and it will be as we start using more biomass for heating, is this smoke plume. You know, this is a case where you can see there's no snow on the ground, but this person was still running the furnace, and when the damper shuts, you have a fire going in there, and they smoke. Some of the advantages of outdoor wood boilers, though, are they can use low-cost fuels. Wood scraps, pallets. I've already talked about being cheaper fuel. What is the true cost? And one of the issues with these is sometimes when people are trying to figure these, look at these, they don't look at the true cost of that fuel. You have the opportunity cost. You could sell that, if you're cutting the wood, you could sell it to somebody who's going to burn in the fireplace, possibly for more or at a higher rate, and then buy pellets, for instance, basically with burn cleaner at almost the same price. So high emissions and smoke is a problem. Now, you can handle this by some management issues. When it's going to be a warm day, you don't put as much wood in. You stoke it at night versus in the morning when you're not going to have the fuel use. Kind of judging on how warm it's going to be during the day is how much fuel you put on it, so you have a smaller fire when you don't need as much heat versus just loading it up and letting it burn. These outdoor wood stoves are pretty low efficiency. In fact, I was really surprised. The EPA has been working on this because of the emissions standard. They have a voluntary program, and when they started testing these, they found that the efficiency of these range from 20% to 50% with an average of about 40%. Stoves today, since 2008, there's a voluntary standard and a listing of the stoves that meet this new EPA requirement. The advantages of these outdoor wood boilers are they're great for heating floors. You can do it with the air exchanger. I already talked about scrap materials you can burn in them. But in some states and some locales, they've actually banned outdoor wood boilers because of the smoke emission problem. The EPA qualified outdoor boilers, they have 90% less emissions. That's a requirement to meet the standard. But one of the advantages, lower emissions equals higher efficiency. We've gone from an average of 40% to almost 70% for the average emissions for this. And some states, as I said, are restricting sales to these EPA-qualified stoves. Unfortunately, Wisconsin is not one of those, and that's an issue. And I don't know about other surrounding states, but I know in the Northeast, states like Maine and New Hampshire have banned these things. You can go to this EPA website and get more information, Burnwise website, and here's a link to the list of stoves that meet this white tag or phase 1 qualifications. And if you can get a hold of the tag that's on here, it actually has some very good information. We'll tell you the 8-hour rating. So if you typically you load these up and walk away for 8 to 12 hours, and so it will have the 8-hour rating, and you'll find out that these things don't really have that high an output in some cases. You also find the efficiency, and then they talk about the particulate matter, and they have a graphical. This is a graphical emissions comparison between those stoves. So down here we've got emissions, we've got efficiency, and then the particulate matter in different ways of presenting that information. What I'm going to try to push people to is pellet boilers for a number of reasons, which we'll get into. But this is a typical layout. You've got a boiler here in the center. You got a supply bin. There's some kind of an auger to feed the material into the boiler. You'll have some controls here. And then this particular boiler has automatic ash removal, so it's got an auger out, and this greenhouse grower has a little cart here to take that ash away. So they can be laid out very nicely. There are also ones that, this is one that can be used in a residential situation. They come in a furnace or boiler. This happens to be a furnace, and you can tell that because of the sheet metal on top. But again, it has a storage bin, has an auger to feed the material into the furnace, and it will. The nice part about these is if they have a thermostat, they will meter the fuel in as it's needed. Here's a larger corn or pellet boiler. This one's large enough to heat a fairly good-sized greenhouse. One issue is that this may be at one end, and you've got to get the heated air circulated around the whole greenhouse. But another way to do it. Here's an example of one where you've got the new furnace, pellet stove, but I highly recommend you leave the old one because these things do sometimes burn out, or the flame goes out. You have a flame out. And if you have the old system set at a little lower temperature, at least you won't have a total heat out issue. We've already talked a little bit about this, but the advantage is it's homologous fuel. We can use a number of different products. Actually, here's paper, waste paper that's not suitable for recycling. Actually, the state of Wisconsin burns some of that in their coal-fired power plants. You get an accurate feed rate or accurate adjustment of the burn rate. So these can be set on a thermostat, or sometimes they're just set so that you set a little dial and it meters it in. The biggest advantage is low emissions and high efficiency. Typical unit is 80%, and there are some out there that are over 90%. Low labor costs. You don't have to worry about stoking as long as you have a large enough fuel bin. These things will run all night, and some of them even have automatic ash removal. But you do need to look at the labor it's going to take to run these. How do we distribute the heat from these? With furnaces, this could be ducts and fans. Could be polytubes, but it depends on the output temperature. Sometimes you're going to have to use metal. With a boiler, you're going to use this piping picture on the bottom left as an example. Then go to water-to-air heat exchanger, or you can use benchtop or underbench or in-floor heating. And the advantage, if you heard our general energy conservation, basically we can produce a microclimate and actually reduce the temperature we required in the greenhouse for heating. And we get increased worm roots, get increased growth, and increased production, or faster to flower, depending on what you're growing. If you do use benchtop or in-floor heating or under-bench heating, you will often need some other air exchangers around for those very cold nights, because sometimes these systems don't have enough capacity to keep up on a minus 10-degree night. So here's some examples of some air exchangers that could be used to just distribute the general distribution of heat. Here's an example of the benchtop heating. This has got a little microtube on the top of the bench to distribute the heat through the bench, and a supply and return line. So just an example. Here's an example. We've got a big old boiler here, and to even out the peaks and valleys of that, we've got a big water tank here. So the boiler is actually heating the water in the tank, and then we're drawing the water out of the tank to feed our different greenhouses. So the biggest advantage here is that we can run this furnace or boiler at a low rate, continuous, so we don't have a lot of, and that reduces the amount of emissions. If it's burning, the flame is burning hot and steady, constantly flipping the damper on and off. And one advantage of this, you might be able to get away with a smaller boiler because we can level out those peaks and valleys. Wood chip boilers. These, we talked earlier about wood chips being a very low-cost, locally available product. Well, you need a boiler that specializes in burning them. So the disadvantage of these is it's high capital cost and a little higher maintenance. You got quite a bit of moving parts because this is the boiler itself, but this is the feed into it. You just have more mechanisms here. But they are very suited for, a large greenhouse operation. If you had acres of greenhouse under cover, or schools, industrial applications. Here in the States, we've got some cheese plants that are actually burning wood waste for the boilers for steam or process heat. You're using a low-cost product to provide that. You will need labor to feed charge hoppers, depending on how your system is set up. Sometimes they're set up with a totally automated bin where you dump the chips into a bin and it automatically feeds them into a boiler. Others, there's a day bin or charge hopper that you have to fill daily or several times a day to provide the wood fuel supply. You do need storage typically for a tractor-trailer load plus of chips, and you have to look at what the available supply is. That's utmost important to find a supplier so you have a continuous supply when you need it. Another option for greenhouses would be standalone boilers. These are the advantage of low cost. I mean, this is just a residential type boiler. They're easy to install, fast payback, although it just supplements the heating. It won't supply total heating unless you have a very small greenhouse. The disadvantage is the hopper may be too small to last all night, full burn. You can see this grower was pretty inventive. He found an old milk filter hopper here, and he sticks that in the top and fills it. They may or may not be thermostatically controlled, so you could have overheating or supply more heat than the greenhouse needs, depending on what the temperature is. And these don't distribute heat. You've got to have some way to push the heat around the greenhouse. They are lower BTU output. You look on the market, they're 70,000 was about the largest one I could find in a small standalone type boiler, or not a boiler, these are more of a stove or a furnace. So but they're efficient. They're 80% efficient if they're well maintained. Here's another picture of one, a little larger unit. Again, it's sitting in here, but we've got to find a way to move that heat around the greenhouse that's going to give off. Now to kind of bring it down to dollars and cents, because that's what ultimately is going to make or break a project. We've got top, I've got corn, and what I've got here is the energy content, basically in this column. I've got boiler efficiencies, and if they're in parentheses, that's what I used for the calculations here. I got the fuel cost, and that's a moving target. I think this was as October 2008, but actually I think we're probably, with the exception of corn, I think we're probably in that ballpark still. Well, heating oil is probably higher too at the moment, but who knows what it will be by the time we get to heating season. But this just shows you, a comparison on a million BTUs, the cost per million BTUs, and some things to point out is natural gas is very cost effective. Propane, depending on the price, is up there with heating oil at $2.50, but at $3.50, heating oil is going to be the highest price fuel. Your outdoor wood boiler, if it's an EPA Phase 2, would be the most cost effective based on $200 a cord. So it gives you a ballpark of how of a comparison. So one of the questions is, how do I size my heating system? Well, one thing you could do is look and see what your heaters are now. Typically, they may be oversized. That's typically done. But you can look at it two ways. One, you can do a full replacement, or the other you can do is a partial replacement. And then what you do is you rely on your current heating system to back it up on a few cold nights. When you have a smaller system, they'll run more continuously and be more efficient, so that can be an advantage. Typically, what we find is that about 80%, 50-80% is a pretty cost-effective percentage to replace, but that all depends on the situation. And we'll see some of that when we do the case study here in a minute. A couple slides on waste vegetable oil. This is, we hear, Vegemobiles and stuff like that. And basically, they're using waste vegetable oil from fryers. So it is a good product. It can be used. But my question is there ample supply? There is competition for it in some cases. What's the cost to collect it? Just because the vendor gives it to you free, you still have time and gas to get it. And do you have storage for it? In this picture, and you have cost to process it. It's going to need to be filtered. You've got to get the water out of it, and you've got to get any sedimentation out of it, or it's not going to be burned very well in a boiler. Okay, so we've got two choices with waste vegetable oils. One is you can convert it to diesel fuel or biodiesel, and that requires some processing equipment, and then you can burn it in a standard oil burner. And I'm not going to get into that process. The other option is that you can buy what they call a waste oil burner. You have to filter out the particulate matter and the water, and typically it's going to be a higher viscosity, but it's got a line heater on it to make it work. So that's another option for that. So it all depends on supply. So here's an example of this is a waste oil burner, one that's made specifically for waste oil. In a greenhouse. And if you go to this link, you can find more about this. Was a funded study that this person did it. And I believe you had to have an air compressor as part of this particular unit. So now as we get to our case study, we're going to look at two different size greenhouses. We're going to look at a 30 by 60 or 30 by 96 freestanding, and then we're going to look at about a half-acre gutter connected and see what their options are. So for this one, I used a double poly glazing. I'm looking at spring bedding plants, so February to June, typical spring growing season. The current greenhouse has two 200,000 BTU power vent heaters in it. They're about 78% efficient. I did this one on $2 a gallon propane with a daytime-nighttime set point of 70 and 60, located it's actually just outside Madison. This actual greenhouse. So we looked at a couple different options for this greenhouse. One was option A is a standalone residential shop type stove. It's got a 70,000 BTU output. It's mainly going to be operated at night just to supplement the heat. There's no thermostat on it. Installed cost is $4,350. It's 80% efficient, and we're going to use bagged pellets at $4.20 a bag, or $210 a ton. Now, you could get bulk on this, but then that's going to increase your installed cost because you have to have a bin. Option B is a thermostatically controlled pellet furnace. This has a operating range of 10,000 to 160,000 BTUs per hour, 80% efficient. We're going to have this air ducted into the greenhouse directly above the plants. It'll be located in one end of the greenhouse, so we've got to push that air around. It has a 14-bushel feed bin, so it should last the night. And again, we're going to use bagged fuel to avoid bulk storage costs. The third option we're going to look at is using a EPA Phase 2 wood boiler. This one has an 8-hour rating of 160,000 BTUs per hour. We're going to use 2 air exchangers in the center of the greenhouse, and basically we're going to face in the opposite direction so it works with our horizontal circulating fans in the greenhouse to distribute that air a little more evenly. It's going to be thermostatically controlled, so we're going to have a pump on it that'll circulate the air or the water glycol solution to our heat exchangers when the greenhouse needs heat. The installed cost, including everything, is about $13,000. It has an efficiency of about 75%. And I'm going to assume $150 per cord, assuming you're going to harvest it yourself and not have to pay profit to somebody. Option D is the same as C, except we're going to use a non-EPA qualified stove. The cost on that is about $11,600, and it's 40% efficient. So that's kind of what we're going to use for the options. Now, how much heat can we get out of the greenhouse? We basically have to heat February, March, April, and May. So if we look at that, the average heating per hour ranges, and this is just nighttime heating, ranges from 136,000 down to 28,000. So February is the real month we have to look at for sizing the greenhouse. But we can look at the other months as to how much we're going to get out of that. So the daytime heating needs, on average, can be met fully by solar radiation. Of course, it's going to vary. Some days you'll need it, some days you won't. But it will usually be less than nighttime heating needs. So we're going to kind of ignore that at this point and just assume that we're going to need some heating in February, about 13,000 BTUs per hour. So how much biomass heating can be provided? We've estimated for option A, which is the standalone stove, 100% of the heat can be provided down to 40 degrees. We look at, I did this basically with a model to look at the heating requirements, and then we're going to estimate about 50% reduction in propane costs based on that. The other options, we've got 160,000 BTU boiler or furnace, and we're going to be able to supply 100% of our heating down to about minus 10 degrees Fahrenheit. Well, on average, the monthly minimum temperature for February is about 14 degrees. Well, we know in reality we can't provide 100%. There's always going to be some time when we can't. So that's based on the averages. So we're going to assume that in reality we're going to need propane about 20% of the time to meet those really cold nights and maybe some days earlier in the season when it's not worth starting up that stove for a few hours. So when we crunch all the numbers, we've got the system cost, we've got the amount of biomass we need, the cost, the amount of propane we need, the propane cost, and the total savings. Total savings is based on using all propane, which is up here in the top, about 16,000 gallons at $2 a gallon, almost $3,200 a year. And then the simple payback is basically this savings number divided into the cost of putting in the system. So on this first one, it's $4,250 divided by this $722. So you can see we have anywhere from 11-year payback to 5.7-year payback. So probably a little longer than a lot of growers would like, but it is very sensitive to the relationship between fossil fuel costs, depending on which fossil fuel you're using, and cost to secure the biomass. One thing I want to show you here is that the EPA, the EPA stove, outdoor stove versus the non-EPA, you can see it's well worth buying that rated stove based on these paybacks. But this is still higher, basically because of this higher cost here than just buying a smaller pellet stove, even though the cost of the pellets may be more on a per pound basis. The second piece of our case study here is a gutter-connected greenhouse. This one happens to be in a T-shape. The one I modeled it, it's 3,300 square feet. Double poly film glazing on the roof and walls. This has got like 14-foot high walls on this particular greenhouse. Year-round production, so heating in the fall as well as the spring throughout the winter. You've got in-floor heating in this greenhouse with peaking units for those cold nights. $2 gallon propane. So based on our model, we found that this greenhouse is going to use about 85,000 BTUs or gallons of LP gas a year, or about $71,000 a year. So that's a pretty darn hefty bill to the fuel company. We're going to look at we're going to look at some options here, but this first one would be to use an outdoor wood boiler, which is very popular. We could use the best, which is 75% efficient. We would need 389 cords of wood. Well, that's a lot of handling, a lot of labor requirement. This particular grower doesn't have a wood lot that could supply that kind of wood because he didn't have a free fuel source. So we didn't include that in this analysis. It just wasn't going to be viable for this particular operation. So we're going to look at pellets for this operation. So here's his requirements on a average nighttime temperature, and what you're going to find is that January, February, and March are the highest months. Basically, you need about 2,600,000 BTUs per hour to meet the average heating requirement for this particular greenhouse. So we used those. We based we did a design temperature down to minus 20 degrees, and that's basically based on some recommendations by the National Greenhouse Manufacturers Association, and found out the heating requirement based on heating demand for the biggest design, if we want to replace 100% of the fuel, which this grower wanted to look at, was about 4,200,000 BTUs. So what I'm going to try to show in this is the difference between 100% replacement and partial replacement. So option A, we're actually going to use two furnaces so that we can look at middle of the winter versus spring and fall. So we looked at what was recommended was a 3.5 million BTU per hour boiler and a 1.5 million BTU hour boiler. The average efficiency of these is 78%. We're going to use that small boiler in the spring and fall, and basically having two boilers, we can throttle them depending on what the demands are. We're still going to assume that we're going to need about 5% of the season we're going to use propane. One, because you're going to have some time when it's probably, even with a small boiler, it's going to be too big to throttle down for some times without overheating the greenhouse. And we're going to have a backup anyway, possibly. So we're going to have bulk bins for bulk delivery of the pellets, and this was going to cost almost $300,000 for this particular operation. So a good chunk of change again. Option B was to try to just meet the average heating requirement. So we downsized this. We have a 2.5 million BTU boiler and a 1 million BTU boiler. Again, the smaller boiler will be used in the spring and fall. So just to try to meet the demand a little better, we assumed here we're going to use 20% propane. Again, bulk delivery of pellets. This reduced the cost to $211,000. So this is the kind of operation or boiler we're looking at putting in here. I showed this picture earlier with a bulk bin. The bin needs to be sized, depending on your delivery vehicle, needs to be sized for about 125% of your bulk delivery to 150% of your bulk delivery. That's the kind of boiler we're going to use. So here's the numbers, because the economics is what really matters here. So here's the amount of pellets we're going to use, the pellet cost, and I think this was based on, well, let's see, I didn't put the fuel cost in here. I think it was based on like $175 a ton delivered. The propane cost and the energy savings. So you're going to find here, both these are actually excellent paybacks. You know, anytime you get under 4-year payback, that's 20% return on investment. So both of these are excellent paybacks for this particular operation. Just a point here, you know, when we look at energy efficiency or doing a biomass project, one of the things that you really should compare with a biomass option, if you want to look at biomass, is the energy efficiency options to reduce your total energy requirement as well. In this particular gutter-connected greenhouse, this person also had natural gas available, but he wasn't using it. And if he had converted his greenhouse to natural gas at the current costs, he could have saved $90,000 a year just on fuel costs, just by converting to a lower cost fuel, which was already available. And then he could take that $90,000 and put it into, say, an energy curtain to reduce his costs even further. So here are some resources that you may find advantageous. There's 2 companion bulletins here on basically on this presentation. There's a biomass boiler or biomass calculator looking at different biomass and replacement versus fossil fuel. This is a website that one of my groups worked on. So you may find that. There's some fact sheets that focus on energy, which is the Wisconsin Energy Efficiency Program. Also, Iowa State has some very good bulletins on theirs. Here's something on from Penn State on burning shelled corn as a renewable fuel. So those are some resources that you may find advantageous. And with that, that's the end of the presentation. This, as I said before, this presentation was a grant from SAIR, the North Central region of SAIR, Professional Development Grant, basically to help folks out. So are there any questions? If you would like a copy of the PowerPoint itself to use, which you're welcome to, if you can send me an email, I'll send it to you. It's about 30 meg. So what I'll probably end up doing is putting it up on a FTP site where you can download it. So if you'd like the PowerPoint, I can get that to you as well. And you're welcome to use the PowerPoint either all or part to fit your needs. Okay, I got a question. You presented on curtains and now biomass combination seems to decrease heating costs. What about earth contact in combination? Earth, I think probably referring to like earth tubes or thermal storage. That's certainly an option. I know there's a grower in Nebraska that's done it. Did it for many years. You can bury tubes in the ground, say under the frost line, depending on where you are. Up here in Wisconsin, it's probably be about 7 feet deep, and you can heat the air to about 50 degrees through one of those earth tubes. So that can supplement your heating possibly, but for a commercial greenhouse, you're going to want less fluctuation of temperature, so you get the product to market in a schedulable time. That tends to be one of the issues. But certainly for makeup air, it would be a possibility. Or if you're doing say you're doing a cold frame in the wintertime, you're trying to grow, say, spinach, that's a possibility. There is some information in a Midwest Plan Service book that Joanna said, send me an email and I'll dig up the reference for that on EarthTube if that's what you're interested in. Any other questions? You can unmute and talk too if you'd like. Well, seeing or hearing none, I think we're probably finished for today. Remind you that we have other presentations later this week on Thursday and next week as well. So if those topics interest you, please log on. I'll be sending out a post-evaluation. We really appreciate if you fill those out to give us an idea of how effective our program was. Have a good day.